Hello everyone, this is the solution video to quiz 3. Now, the question was to convert the magnitude phase omega vectors using the amount of delay tau into the delayed magnitude and phase vector theta. Now, in order to do that, we were only allowed to use simple addition, subtraction, multiplication, and division. And well, how can we do that? Well, basically, the function is given here. Let's directly jump into it. Now, since the only thing that we change here is basically the amount of delay that we add, we're going to examine minus tau times s, both in magnitude and in phase. So the important thing is that we use the argument of this and the magnitude. Since we are using the frequency domain, s equals j omega is the Fourier transform, so let's plug in s equals j omega, and that's basically it. Now, you might want to use the Euler identity where you use cosine squared or direct cosine minus tau omega plus j sine minus tau omega. And if you take the magnitude of that, since we have cosine and sine, their squares is cosine squared plus sine squared, and that's going to be equal to 1, and the square root of 1 is 1, so we actually don't change the magnitude at all. So we can directly use mag d, the delayed magnitude, is going to be the magnitude itself. So that's one thing. On the other hand, we have e to the power of minus tau j omega, where minus tau omega is basically theta, and we're looking for the argument of this phasor form, which is basically minus tau omega. If you think about cosine theta plus j sine theta, theta is the question and it's tau omega. So basically it should be looking like this. Now, since we use the argument a plus b can be decomposed or calculated via the argument a plus argument of b. In that regard, what we are going to do is we are going to say phase d is going to be phase minus tau times omega. Now the issue here is the following. This is not the final answer. Since omega is in radians per second and tau is in seconds, so it would be radians. Whereas phase and phase d, since this is the Bode data here, is going to be basically in degrees. Therefore, we need a little conversion, which is times 180 degrees divided by pi radians. So now we actually completed the task here, because this would be then the result. Now let's dive into the test script, where we have a certain system and a certain amount of delay, and we're using the Bode function directly to calculate or obtain magnitude, phase, and omega vectors. Once we have that, we need to get rid of the extra dimensions using squeeze. It's not that big of a deal. Then we call our function that we've coded just now, and we basically obtain mag d and phase d. Now we have a figure, the Bode plot style, and we plot the magnitude, phase, and the delayed version. Let me just comment this out and run our script. And as you can see, this looks to be correct. Why should this be correct? Well, visually I can see that this tends to minus infinity, because we have omega, and if omega tends to infinity, it should tend to minus infinity. This actually looks like something that would have delay in it. Now, in order to be correct and validate this, we are going to use basically gs times just gain 1 e to the power of minus tau s, which is IO delay tau. If we add this amount of delay and obtain magnitude, phase, omega again, and then need this extra step here and plot it with, let's say, red and dashed lines, if this will be on top of the blue plot, then it would say that this is a valid calculation. The results are correct. And indeed, we have this overlapping here. So this quiz is quite easy if you don't forget to convert this. And this is actually given for the fact that if you are in a final exam, for example, if you're in a classical exam, sometimes the raw Bode data, magnitude, phase, and omega in this case, is given to you via a table or even the Bode plot itself. And then in the questions that you are going to answer, there might be some delay that's needed to be added to the body plot. So if you were in MATLAB, you need to maybe update it using the delay times the transfer function and then use the magnitude phase plot of the new resulting body plot. Or sometimes we add some p-type controller gains to the body plot. You have to update your body plot. In that case, it is not that difficult to obtain the new phase data, the new magnitude data. The most difficult one looks to be this one, which is basically phase minus tau omega times 180 divided by pi. But keep in mind that this line here is very simple because we're coding in MATLAB. If this would have been coded in C, we need to use a for loop. So this is basically, if you have a table, this is a row by row operation. You have to look up the ith value of phase, the ith value of omega, and then do this calculation and just write it down to the phase, the ith element. And you should repeat this for each row. So if you have a certain table, you might want to add another column if needed. And for example, in this case, this would be the delayed version of the phase vector, and you would just calculate each row and you have the newly obtained body plot. So this is just a reminder for that. If necessary, it doesn't necessarily mean that you should have to do this. You might want to opt for this kind of a solution. So keep that in mind.